Okay, so I think we can start again our session. The next speaker is... Okay, so I think we can start again. The next speaker is Rackovic, which is a student in Lisbon, IST. Who is working like G before with Trilateral from Novi Sad. The title of his presentation is Increasing the Accuracy and Interpretability for Inverse Rig Solutions in the Human Face Animation.
Hello, everyone. I can share my screen just a second.
Yes.
Sorry for this.
Is working.
Okay, so I'm working with Claudia Soares, that is now at Nova University in Lisbon, and with Dusan Jakovetic, that is at University of Novi Sad, and with Zoranka Desnica from Trilateral Company. And we are working on solving the inverse rig. So let me first give you some hints about the blend shape animation and the problem that we are facing. So usually in this case of facial animation, we have a mesh that is what we see. This is like a 3D representation of the face, and then we also have controllers. You see, there is like for realistic faces, there are like hundreds of these controllers that are usually set by hand. And this is like a lot of work for animators. So the idea is to try to find some automated way for doing this. And especially in facial animation, the controllers are modeled as blend shapes. So what are the blend shapes? We need to vectorize those meshes that we see. So for example, the mesh consists of vertices in 3D space, and each of them has 3 coordinates. So we take the coordinates and stack them one after the other, so x, y, z, to build a vector that represents a mesh. And now we have a neutral face. This is the face where no expression is shown, so all the muscles are inactive in a sense. And then we also have atomic deformations. So for example, here we can see that the eye is open more than in the neutral phase. Then we have like pull of the corners of the mouth or closing of the eyes, and etc. So we can have hundreds of these atomic deformations, and we also vectorize them in the same manner like neutral phase, and we can add them on top of this to produce the desired expression, or we can combine them to make more complex expressions, which is actually what is done to build an animation. How does this work? When we have these blend shapes, those vectors of the neutral and vectors for each of the deformations, we first extract deltas, which is in fact the offset between neutral face and one of the blend shapes. And now in the linear model of the blend shapes, we simply take the neutral face and add those deltas, those offsets on top of it. And for each controller, we have corresponding weight. So we can set it to 0 if we don't want to activate, or we can set it to 1 if we want to activate the blend shape. But we also can set it anywhere in between, which is adding like for different levels of activation of the regions. And now this also can be written in the matrix notation. In the matrix notation, where the weights are set into a single vector V, and we have blend shape matrix B that is in fact consists of the blend shape of the delta blend shape vectors that are set as columns of the matrix. Now this is linear blend shape that's usually used, that is used almost exclusively in literature. But in fact, in more complex models, there are some corrective terms that add nonlinearity to the blend shape function. For example, it happens if we have 2 blend shapes that affect the same region of the face. they would often produce some artifacts if they are activated together. So like we can have some cracks or some non-realistic deformations in some of the regions. And then if the animator expects to get some shape when activate them together, we can define that shape as this behat, and then if that is different from what it really gets, the artist needs to sculpt this by hand, and then take the difference between expected and obtained mesh, and this is now called the corrective term. So whenever these two are activated together in the future, they also need to involve the corrective term, and it's involved with the product of the weights that are corresponding to these two blend shapes. So now we have this quadratic term. Also, if the model is complex enough, it can have corrective terms of higher levels, like for triples of the blend shapes, or for 4 or more of them. And also there can be some of the non-linear deformations, but we don't include them here in this work because we can see that just adding quadratic terms significantly reduces the error. So what we see in this picture is if we use the linear blend shape approximation, we take the animation data that we have and plug in the weights using the approximation with linear blend shape function, and these are the red dots. And then just for the sake of the clarity, this is if we have a zero weight vector all the time. So if we approximate each mesh with a neutral phase, just see that these errors that linear model produces are not neglectable. And then if we include quadratic terms, we see that this is reduced almost to zero, which is good enough precision that we can work with that, and we don't want to include much more complexity in the model. Now, inverse rig problem is in fact once we have the mesh, so it's usually we have 3D scan of the face of the actor or something, and we denote it here as a behat. So once we have this mesh, we want to estimate what would be the optimal weights of the parameters that would produce such a mesh. In this case, f is a rig function, no matter if it is a linear blend shape, quadratic blend shape, or some other rig function. And in the literature, there we here show two different approaches. One that is given by Setin Aslan 2 years ago, and this is like state-of-the-art approach. A lot of other papers have either the same or similar objective function. So rig function is linear, and then there is also this quadratic term, quadratic regularization term. This is used because the solution to the blend shape is not unique. We can have, for example, two activated components that are mutually exclusive. For example, moving the corner of the mount up and moving the corner of the mount down. If they are both activated, the corner of the mount would look like if it was not moved at all, but we have redundancy in the controller. So this should solve that problem. And then another approach is given by a bit older paper. In this case, again, we have a linear blend shape function, but each of the controllers is visited once at a time and solve for it. And we update the residuals after solving for each controller. And in this case, it's crucial to mention that the order in which controllers are visited will influence the result a lot. So for this, authors also propose to order them based on the overall deformation that each of the blend shape produces on the mesh. but also that that means that we need additional steps in the algorithm. And authors also propose some kind of phase clustering that is that is mainly done by hand. And as I mentioned, all of the blend shape models used in the literature are linear, and this is usually good enough for the simple models like this. For example, usually the mockup, which is motion capture of the actor, demands set of the markers on the face of the actor, which is source, and then on the target, set of the motions, the set of the motion markers that correspond semantically to the same points from the face. But the two faces have different proportions, or sometimes this is not even a human-like character. So we cannot expect to have a huge accuracy. And for this reason, linear blend shaped function is good enough. But we work with the more realistic characters, as we saw here. These models are made based. These models are made on the actor, so they are very accurate, and we need a much higher level of accuracy. And we don't use actually markers. We use all of these vertices in the face, and there is like more than 4,000 of them. So for this reason, we include these quadratic terms. We ask for higher accuracy. And also we have this strict constraint on the weight vector W. The values cannot go outside of 0-1 interval. And this is also one thing that the other authors didn't include in their models, because they allow for exaggerated cartoonish expressions. Now we also add different regularization term. This is similar to L1 norm because we have this non-negativity constraint, and this should ensure that the resulting vector is as sparse as possible. This is desirable because usually animators later need to adjust the results by hand, and if the vector is far from sparse, it's very hard to work with it. So sometimes they need to start everything from the scratch and do by hand. So now using this quadratic model under the square norm yields a very complex problem. So we have idea to approach this in a different idea, like applying majorization minimization. We need a surrogate function that is simpler to solve than this original function. And we also approach in the optimal increment manner. So instead of finding a single vector, we look for the increment, and we do this iteratively. So in each iteration, we get more accurate representation, which demands that we have initialization of the vector omega of the vector W, and there are some strategies that we'll mention later in the results session. Now, I will not go into details for derivation of this surrogate function. We will have this probably published this year, so you can see the details. However, this gives a model that is simple enough to solve. That gives, if we approach the solution component-wise, which is solving for each blend shape, similar to that problem that we saw earlier, then we have a closed form solution, and we can have relatively quickly to compute. Still, this is not done in real time, but this is fine because we are working in post-production for movie industry and gaming industry, and we can afford some delays in the results. Now the results that we simulated are done over 3 realistic animation data sets. All of these 3 characters are available at the platform MetaHumans, as well as other like there is hundreds of other choices. So we chose this because it's publicly available, and the user and the reader can try to recompile the same experiments with it. Now, as I mentioned, we have different initialization choices for the vector. One choice is to use zero vector as initialization. This is good because it will give a sparser result. But then we also have something that we call a pseudo-inverse solution, which is in fact a solution that is obtained in a closed form if we would use linear instead of quadratic. And this is in fact equal to one of the previously showed results. And then from there we start applying quadratic function to get more accurate solution. Now we benchmark our model with let me get back here. We benchmark our model with these two, but as we mentioned here, the autos didn't include constraints on the vector W, which is very important to us. So we need to add them here. Now, if we want to still have this solution in closed form, we can get the solution as our authors did, and then just clip the values of omega to 0, 1. And we will call this set. So this is only this. And then we have also this with CVX because we have other possibility, which is solving this problem using CVX pi, but we include the constraints. Another thing that these authors propose in the same paper is making this matrix B more sparse. This is done with a heat kernel, and the idea is to exclude the effect of the blend shapes that are less relevant for each of the vertices in the face. And that's usually preferable because it would give a sparser solution and maybe higher stability. So we call this localized solution, and we have it here again. We can have a closed form solution and then clip the values, which we call set lock. Or we can solve it including the constraints from the beginning, which we call set lock CVX. And then we have the other one, which is this component-wise optimization, and we call it cell. Also, we work with different values of the optimization of the regularization parameter to see what would be the optimal choice. It can differ for different characters or for the same character and different approaches. The most important metric that we use here is mesh error, because we are aiming for the accuracy. And we simply compute mean square error between the given mesh, which is B hat, and obtained mesh, which is B tilde. Another important thing, as we mentioned, is cardinality, because we want to have sparse solution. But we also look for the L1 norm because L1 norm can show us that even if cardinality is higher, maybe some of the values are very close to 0, and we don't see that here, and we can probably just exclude them later. In this case, we show how the values of the metrics behave for each of the approaches. So the first plot is for the first character, and this is trade-off between mesh error and cardinality of the weight vector. Our model with zero initialization is the blue one, and with pseudo-inverse initialization is the red one. And we can see that red curve is below the others. Now, as I mentioned, sometimes we have like these very low values that add a lot to cardinality, but not so much on the L1 norm. But in any of these two figures, we see that our curve is always below the others, which means that our model is superior to the previously proposed. And especially this one with pseudo-inverse solution initialization. We also try different initializations like random vector, and any of the solutions of these 5 benchmarks, but this one works the best. Now, if we look at a single frame and results for each of these approaches, one thing that we can notice from the beginning. So this is the original, and then we have all the approaches. We see that these two localized model then don't perform so well, so we can exclude them from the further discussion. And also our model with zero initialization, although it gives a sparse model, it usually have less accuracy in the mesh. So also one thing that we notice from a lot of example is that these two, so Satin-Aslan solved with CVX or with a closed form solution, is usually very similar. So we keep only this one because it's much faster. And we can see that yes, our solution, this one, pseudo-inverse solution, has a higher accuracy. It's a bit hard. We are trying still to figure out how to present this in a more obvious manner. But we see that, for example, in this region, we are more accurate at Satin-Aslan. And also we can see that, for example, here cell has a lower lip that goes over the upper one, which is different from the original, and this doesn't happen in our or in the previous Satin-Aslan model. Now for the second phase, again we see that our curve is below the others. So again we have a superior performance in terms of both mesh and cardinality. And here again, so here we only consider the four approaches that I mentioned. We see that they are all a bit different from the original, but still our model is better depicting this corner of the mouth than the others. And also we can see that cell is opening the mouth slightly too much. So we can conclude from also other frames that we visited that is not very good solution, although it's sometimes very close. It has much higher number of controllers activated and also the values of the activated. So we are actually interested in benchmarking with this one. But again, we still have higher mesh accuracy, which is very good. And then similar for the last character, again, our curve is below the other. And here again, it's very hard to see the difference by a like naked eye. But we can see that we have here a lower number of controllers, and also the mesh is slightly more accurate. So we can conclude in total that our model is superior to the previous works, and that adding that complexity of quadratic approximation of plane shape pays off in terms of the animation of the accurate models. Only thing where we are inferior is execution time, but in the case if we don't need a real-time solution of the model, we can notice that our approach is better than the others. So that's it. If you have any question or suggestion, it's very welcome.
Thank you, Stevo, for your presentation. So are there any questions from the audience? Okay, we have a question. I have to activate the microphone of Giovanni Naldi. Let me find it. Okay, yeah. Okay, Giovanni, I think you can open your microphone and ask the question now.
Thank you for presentation. I have two curiosity. The first one is the following: as in your all regularization approach, there is a hyperparameter alpha. So you have a very several order magnitude of alpha. So you have some int because you come from 001 to 50. So there is some heuristical recipes about the choice of alpha or not.
Well,
because it's a typical problem in regularizations.
Yes,
approach.
so we don't really know. We don't really know what would be the optimal value beforehand. But the thing is that we noticed that there is not much difference if we take values that are below 2. So we can say that around 2 there is like that point where regularization plays important role. And of course, if we go up to 50, I mean, this is added just for the sake of completeness. But if we go up to 50, it's very close to 0 vectors. So we are just punishing this non-sparsity too much. So we should probably be in the region between 0 and 10, and optimally somewhere around 2.5.
The second question is a curiosity. So when you show the comparison between 0, linear and quadratic, okay, I don't know if it's a nightmare from a point of view of coding, but it's possible to consider some adaptivity. I mean, so in a previous slide, you compare the error between 0 and, okay, here. So it's possible from 40 to 50, more or less red and green points are overlap, more or less. So it's possible to, I don't know if it's possible from a coding point of view, but in some sense, to have some index, some activity indexes say, oh, okay, it's possible to use linear, or it's possible to switch to high order approximations. I don't know if it's possible to do something like that.
I mean, I don't know. I guess it would be possible. I don't know if it is worth the effort, because so as we can see, I added here for the sake of comparison, just what would happen if we approximate given frame with a neutral phase. So in this region where these two are similar, we see that neutral phase is not so much different from the given. So that actually means that we have something with very low activation. And I think that's the reason why the difference is so small. So probably we can add some step that would see how different the given frame is from neutral. But I think that would add for computation that doesn't save time.
Okay.
We are switching.
Okay, thank you.
You're welcome.
Thanks. So are there other questions or comments? No, it seems not. So I thank also Stevo for his presentation.
Thank you.
And I leave the word to Rosario because she will, hopefully, if internet works, she will chair the next session. The microphone is not open, sorry. Okay, no. Ah, you should be already allowed, so let me check. Sorry, but yes, because you lost the connection and so, okay. Okay, now you should be able to unmute, okay. Yeah, but we cannot hear you. You unmuted, but we don't hear the audio. No. So no. Let's You can try to reconnect, maybe go out and connect again. Now I changed the security permission so that everybody can activate his audio and share the screen. Hopefully it will not happen, but no, you are still not working with the audio. I don't know why.
Probably a problem with the microphone.
Yeah, unfortunately, yes.
So you can share with the chat.
No, okay, I can substitute Rosario if needed.
Rosario, you probably have the wrong microphone selected in Zoom.
Says no. What
Oh,
about
yes.
Yeah.
Now, yes, it
I'm
works.
sorry. So after this difficult initial period, I would like to thank you, Professor Mario Figueiredo, for accepting to be an invited speaker in this workshop. Professor Mario Figueiredo he's a professor here at Instituto Superior Técnico from the Department of Electrical and Computer Engineering. He also a member of the Telecommunication Institute, and is also a very interesting position here in IST as a FIDSI professor. So FIDSI is a startup on machine learning, and there is this strong link between this company and the university and the research, and Professor Mario is doing this link. Is also a highly cited researcher and appears in the list of the most cited researcher by Thomson and Reuters. Is also organizing from 12 years a Lisbon machine learning school, which is very popular with hundreds of people every year. And he's also coordinating the Master on Engineering and Data Science here in IST. And today he's going to talk about dealing with strong correlated variables in supervised learning. Thank you, Mario, for being here.
Thank you, Rosario, for the nice introduction and for the invitation. Can I share my screen? Is it visible?
Yes.
Can you see is it in full screen?
Yes.
Yes.
Good. And can you see the mouse? That's the last question.
Yes.
Thank you. So thanks for the invitation. This is not new work, although it spans a couple of years. But I think it's still interesting I like to talk about it because it's I think it's of general interest for in many different areas. So I'll be talking about how to deal with strongly correlated variables in supervised learning, which is a prevalent topic. And I have a lot of slides, as you can see, but I will not cover everything in the slides. So I'll begin by briefly talking about feature selection for supervised learning, how to deal with correlated variables and what we mean by correlated variables exactly and why they are problematic or may be problematic. Then I'll talk a little bit about these ways that we studied to address these problems. I'll talk a little bit about analysis, things that can be shown about these ways of regularizing. Actually, I'll skip one of these two because it becomes a bit messy. And then I'll talk a bit also about optimization aspects, because when we have a new regularizer, we need to be sure that we can deal with it in terms of optimization. And if time permits, in the end, I'll talk a little bit about some more recent extensions and applications for this. Okay, so as I'm sure you all know, so you know what linear regression is. I'll just very briefly to set notation, I'll talk a little bit about what linear regression is. So we have n vectors of p features, so this is classical n in p, number of points, dimension of the feature variables, of the explanatory variables, depending on whether you're a statistician or a machine learning person, you call it different things. And then you have n responses, which in the simplest case are just real numbers, and you model the responses as some offset plus some linear combinations of the variables plus some noise term. And this equal sign here is wrong. And you do that for n samples. And the goal, of course, is to estimate the regression coefficients. Without loss of generality in this talk, I will assume that the offset is 0. And as you know, there are many ways to make this work without losing generality. The noise is often assumed Gaussian IID, although it's not necessarily so always. And in fact, this has a very well-known vector notation. A vector of responses is just a linear combination of columns of this so-called design matrix, plus some vector of noises. And this design matrix is just obtained by stacking all these sample vectors. And then, of course, the goal is to estimate beta, the coefficient vector, the regression coefficient vector from y and x. And you can do something similar for logistic regression if you're interested in classification, where what you're after is the probability that each sample is 1 given x, given the variables, the explanatory variables. And this is usually done by formalizing these as some linear transformation, some linear combination of the features. Then go through this nonlinearity, this logistic transformation that makes it, that squashes it into the interval 0, 1 so that it becomes a probability. And again, same goal, same notation, same everything, just a different loss function, a different objective function. So here, this is just a picture about what linear regression and logistic regression, they're very similar in this classical case. Of course, just to keep notation simple, I will consider these x's to be the vectors of explanatory variables, but they could themselves be functions of other variables. So this will include nonlinear regression in the input in x, but it's still linear in beta, in the coefficient parameter. So questions related to feature selection are all these variables relevant, or are some of them irrelevant? Should I ignore some of these inputs and still do well? Which means, should some beta hat j's be 0? And the other question is, are there redundant features? So are there features that are relevant, but redundant in the sense that if I have one, maybe I don't need the others? So these are the questions that are addressed in feature selection problems. And there's a huge literature on feature selection. Of course, it goes back at least to the 80s, maybe even less before that. And there are 3 main classes, which were this taxonomy was first proposed by Das in 94. And it goes like this. So we have filters. Filters just look at the features and ignore what method will be used to what the features are going to be used for. And so what learning algorithm will be used. And so they try to, just by looking at features, to select the ones that are important. And these filters can be supervised or unsupervised, in the sense that if you use the responses or not, or just use the features or the variables. Wrappers are methods that, so as the name implies, are wrapped around some learning algorithm. So you use a learning algorithm to estimate your parameters, and then you assess the quality of those, each feature subset, by using some learning algorithm to actually use those features. And then you have some selection methods, some optimization, outer loop wrapped around some learning algorithm. And then the embedded methods, which are the most commonly used today, and more interesting from my perspective, where the selection is embedded into the learning algorithm itself. And this is usually done by invoking some regularizer. We already heard about today in previous talk, actually, some sparsity inducing regularization. But in general, so the idea is that you can formulate your regression problem or your learning problem as a minimization problem, where you trade off, you try to minimize something that has 2 terms, so some loss function, usually in this case, it would be like for the regression could be the squared error loss, and some regularizer. And this, of course, this loss is a sum across all your samples of some loss that measures how well or how bad you're fitting your response y at point x, y, given your current estimate of your parameters beta. And so this trade-off between these 2 things will yield a solution. And the reason why this is a nice way to tackle these problems, as you know, is that this is usually solvable, although sometimes we need to spend some effort on devising optimization methods to solve these problems. And because the solution is a minimizer of some objective function, we can analyze the solutions. So it's solvable and analyzable, and so this is why it's good to formulate problems as optimization problems, learning as an optimization problem. Okay, so the classic method that everybody knows, and we've seen instances of these today already, is using the squared error loss, where you implicitly assume that the noise is Gaussian and additive and IID and everything like that, and that you know the variance. With although I'm sweeping the variance under the rug because it can be absorbed into the regularizer, and then there's a regularizer. And if we use squared error loss, we know how to solve these. This is famous ridge regression. Goes back to the 70s, actually, in signal processing and control. It goes back much earlier to the 40s, to the work of Wiener. And of course, the new classic that I'm sure you all know, which is lasso, where instead of the squared Euclidean norm of beta, we use the one norm of beta, and that is known to induce sparsity. So sparsity here in this picture means that the solution of this problem will tend to have, in certain conditions, will tend to have solutions that are exactly on some axis or coordinate planes, which means that the other coordinate is zero. So it yields sparse solutions. And this is well known, and I'm sure you all know it. So this can also be done for logistic regression. I will not spend time here explaining what logistic regression is, but I'm sure you all know. It just means that you need to use a different loss. It's called the logistic loss, which is still convex, such as the other, although it's not strongly convex. And the idea is the same. Okay, we can still use either squared Euclidean norm as a regularizer, and you get ridge logistic regression, or you can use the L1 norm and you get sparse logistic regression, which goes back at least to the 90s. Although this problem is much harder to solve because of the non-differentiability of the L1 norm. Okay, this can be extended to many other generalized linear models, as is very comprehensively covered in the book by Bullman and Sada van der Gier from 10 years ago. Okay, so now let me get to the issue of correlated variables. Okay, so why are correlated variables relevant? Why don't we just get rid of them in some way? So suppose that the goal is to identify all the relevant variables, regardless of them being correlated or maybe redundant. Okay, why would you want to do this? Well, in one situation is when your variables have meaning. Suppose you're trying to predict a disease from gene expression data. This is just a toy picture. It's not real. Well, it is actual gene expression data, but I'm not going to use this data just to illustrate the idea. Suppose you have like tens or hundreds of samples, so n is reasonably small, but p, so the number of features is very high, so thousands. It's typically a situation in say gene expression data, and you want to apply supervised learning, say logistic regression, to learn how to classify a disease from this data. Okay, because you have, so if you have a lot of features, of course, too many features in a sense, you want to use some feature selection method. You want to use some regularizer, for example, that induces sparsity. And what happens is that the genes, let's say, that are selected, you don't want just to select the ones that are good for prediction. You also want to know which genes are selected, because that may have scientific information. It may say that these genes are expressed in this disease. And so even if several genes are co-expressed and very, very highly correlated with each other, you just don't want to throw away a few of them and keep one of them, which is good enough for prediction. You just want to keep them all, because that will have a meaning, will have some scientific meaning. Okay, so this is the idea. You not only want to optimize prediction, so the ability to predict your disease, but you also want to identify all the involved genes, because that may have important scientific information. Okay, the problem is if you naively use lasso in a situation like this for highly correlated features, you end up, and this has been studied quite deeply by Peter Bullman, you end up with an arbitrary subset of variables, because this is very unstable. So this picture kind of illustrates the idea. So suppose that you have, in this case, in this picture, your design matrix X would only have two columns, so you're only dealing with two features. But of course, the situation is more general. Just for illustrative purposes, suppose you have two columns of X are extremely highly correlated. Okay, so they're almost collinear. So what happens is that the level curves of this term, of the loss function, are these very, very narrow ellipses. So this is, and as the correlation goes to 1, this will become essentially a straight line at 45 degrees, if you're assuming that the columns are normalized. And so when you're trying to solve the regularization problem using an L1 norm, which is equivalent to solving this other problem, which is you want to minimize the loss subject to an upper bound on the L1 norm, they're equivalent because everything is convex. What you end up is with the situation where the level curves of the reds, these red level curves, which are level curves of this term, and the level curves of the L1 norm are essentially parallel. And so the point where they first touch is extremely sensitive to minute details in the data. And so sometimes you end up here, other times you end up there, other times you end up somewhere in the middle. And in the extreme case, where this is perfectly correlated, two columns are perfectly correlated, the solution is, the objective function is flat in this line, and you get, depends on the optimization algorithm that you use, you may end up in a different position. So any convex combination of these two points would be an equivalently good solution from the perspective of the optimization criteria. And so, of course, this is an undesirable situation. And to address this, people have come up with different strategies. So one of them, which I'll probably skip, is to, well, I can talk about it very quickly, is to actually skip things that statisticians do very often, which is once you have your data set, you look at the correlation structure of your variables. And so once you do that, if you have a correlation structure of your variables, you can, for example, this is a method called cluster lasso. You can cluster your variables, your features, using this covariance information, using covariance as a measure of similarity. And then you use group lasso, meaning that you group the features in each that are together in a given cluster, or you select one representative from each group. Okay. There's another technique which I'll call graph TV, which I'll skip. But the key aspect is that all of these methods, the way they scale with the data size, is quadratically in T, number of features. And so this is undesirable because if you have lots of features, say thousands of features, just computing the covariance is very expensive. So another class of methods is to slightly modify the L1 regularizer, and this is the first proposal in this direction is a famous elastic net, and which I'll explain in a picture. So remember that the key, so this dashed line here in the middle, this dashed square inside, is the ball of the L1 norm. And these elongated ellipses here are a situation where your loss has very highly correlated features. And so the problem again is that this line is almost parallel to this line here. And so you end up with a very unstable minimum or minimizer. And so what the elastic net does is add to the L1 norm, the L2 norm, which essentially inflates the ball. So the ball is no longer a perfect square. Now it's a sort of an inflated square, okay? And it kind of breaks this symmetry along this line because this green line no longer has this property. And the other method, which is the one which is the starting point for our work, is something called OSCAR, where you take the L1 norm again and you add to it this other term, which is the maximum. So the sum across all the pairs of variables of the maximum of the absolute values of that pair, okay? So in 2 dimensions, there's only one of these terms because there's only a pair of variables. And if you look at the level curve of this function, you find out that it's this octagonal shape. And the idea of the key thing of this being an octagonal shape is that it has these vertices exactly here at the 45 degree in the middle of the orthants. And so if you're dealing with a highly correlated situation, a highly correlated variable situation where the loss has these elongated ellipses in the level curves, there's a high likelihood that you end up in these points, which we call grouping solutions, where the coefficients of the 2 variables will be exactly the same, okay, which identify the 2 variables as being both relevant but highly correlated. This is in contrast with the situation where you have only one variable selected, so sparse, and here it's not sparse. Okay, it's both variables are on, but they're equal to each other. So that's the key observation. Okay, so let me just give you an illustration. So suppose this is the design matrix that we have, and just for this is the example, of course. You have the variables are equal in groups of 3. They're all together, but they could be in any other position, just for illustration purposes. And so suppose that your true beta, so the data was generated by just taking this matrix and multiplying by this beta. So only these groups, these 3 groups are active in the actual beta star, the true beta. And then if you use lasso to estimate this beta, you get something like this. Okay, this is not, there's nothing wrong with this. If you want to identify, but there is only if you want to know that all these variables are actually active. Okay, actually, this is one possible lasso estimate. So lasso could also give you something else. It could choose another of the variables. You don't know. It depends on where your algorithm, on the details of the algorithm and the details of the noise. It could give you something like any convex combination of these 3 values would give you the same. It would be equivalent. So you don't really know what it gives you. Although Oscar will always, in the presence of these highly correlated variables, will always give you these solutions where the corresponding coefficients have exactly the same value. Okay, this is all the results by Bondel and Reich, who proposed Oscar. I'm probably gonna skip this. I'm gonna skip this. So just an illustration. This is a correlation structure from some data sets, some small dimensional data set, just to illustrate the idea. Where Oscar identified that these variables that are, where the coefficients here are highlighted in red, they all belong to the same group, in the sense that they all have the same value, meaning that they are all highly correlated, as we can see there. Okay, and there's another variable which is in the same group, but with a negative sign, the same absolute value, but a different sign, which means that they were the equality between the coefficients was here in the, so they have different signs. It's either here or here, in the second or fourth orthant for that pair. Okay. So this was a starting for our work we did in 2014 and 15, and the idea is the following. So it's easy. So let's see. So it's easy to show that it's not moving. It's easy to show that these Oscar can be written in this way. So you can write this norm in the following way. You take your coefficients of the argument beta, you compute the absolute values, and you sort them in decreasing order. So beta absolute value 1 is the largest absolute value of the coefficients, beta, and so on and so forth, up to p. So sorted absolute values. And then you have a linear combination of these sorted values, but where the weights depending on the position after sorting. Okay, so the largest absolute value will take the largest weight, which is lambda 1 plus lambda 2, and so on and so forth. So essentially, it's easy to see that the reason why this happens is that the largest of all the coefficients in absolute value will be the max in all the comparisons with all the others. And so you will take the highest weight, and so on and so forth. And so what we saw is that, okay, why do we have to have this linear decreasing sequence of weights? Why not any decreasing sequence of weights? And that introduced something called the OWL, ordered weighted L1. It's an L1 norm, but ordered. So the arguments are ordered in decreasing order of magnitude, and they're weighted. So it's not a straight L1 norm, but a weighted L1 norm. And so this actually was proposed simultaneously. We had also a paper in arXiv in 2013 by Bogdan and other people with a very different motivation, not for clustering variables, not for finding correlated variables, but for false discovery rate control. But it's the same structure. So this can be written in a more compact way if we denote as this beta absolute value down arrow as the sorted vector, the vector that you obtain by taking beta and sorting the components in decreasing order of magnitude. So just a few words about this function omega. So it is indeed a norm. It's easy to show that it is a norm. So since it's a norm, it's convex and has all nice properties of a norm. It's easy to establish some relationships with the L1 norm and with the L infinity norm, but I will not spend time on that. Around that time, the first experimental results using OWL were done in a large machine translation experiment. This is a PhD thesis at CMU. Now it is completely outdated stuff, but it's still interesting to highlight what is going on. So just think of this as a very, very large logistic regression problem with some, well, it's more structured than that, but that's not important for us now. That has around 1 million parameters, okay? If you just do, say, reach, so regularizing with L2, you get all the parameters are non-zero, so this column contains the number of non-zero parameters, so around 1 million, okay? If you use L1 plus L2, which is the elastic net, you sparsify a lot, so you get something like 75,000, 79, 115,000 parameters. And if you use OWL, you get not so sparse, okay? You get back to very large numbers of parameters, again, not very far from 1 million. But what's different here is that there is almost no parameter sharing. So these 75,000 different parameter values, among these 75, there are 55,000 different values. So there's no sharing at all. Whereas when you use OWL, you essentially do this sharing, which means that these 677,000 parameters share only 922 unique values. So most of these, there are thousands of coefficients that share the exact same value. So this property of weight sharing or parameter sharing is very well known to be very important for deep learning, for neural networks actually. This has been known since the 90s. And typically this is imposed by, say, using a convolutional neural network or forcing parameters to be equal for some inductive bias principle. But what OWL is able to do is to learn this sharing directly from the data, being adaptively weight sharing. Some more recent results using OWL. This is work by Lee and Becker-Willett in Chicago. Again, this is a classification problem. Okay, so the idea is to try to guess if someone with inside an fMRI machine is looking at a face or a non-face. So it's shown an image, either a face or a non-face, and from fMRI data captured from the brain of the subject, trying to predict if we can guess just by looking at the activity in the brain if the person is looking at a face or a non-face. And so the alternative methods here, forget about all the other ones, just look at the blue. The blue is the graph TV regularizer, which I talked about, which I mentioned very briefly a few slides ago, which relies on knowing the covariance matrix of the variables. The variables are just different regions of the brain, which are highly correlated. And OWL is the orange line. And what these results show is that OWL, which has no idea about correlation, is not given the information about correlation and dependencies between different variables, does almost as well, in some cases slightly better, than GTV, which has full covariance information about the variables, about how the variables are correlated with each other. Okay, so this is Oscar, its generalization OWL, and empirical evidence that it works well in certain types of problems where it is known that the variables are correlated with each other, and it's important to deal with these aspects of the data. So now I'll talk a little bit about analysis of the solutions of this problem, of this regularizer, and I will just talk a little bit about the exact clustering conditions. I will skip the statistical error bound, which is more, say, hardcore machine learning, and I would have time to make justice to that work. Okay, so the tools, actually I like to talk about this because it brings back tools that are nice and that we were not expecting to be using in this area. So the key tools that we use to understand OWL are majorization and true convexity. Okay, so majorization, which is an old notion, is this. So suppose you have two vectors in RP, okay, and we say that vector gamma majorizes vector beta, and it's denoted like this, if the sums of the components of the two vectors are the same, and the partial sums are always dominated by gamma. So gamma is the one that majorizes beta. So the partial sums after sorting. So this is, so for j equals 1, this is the largest gamma in absolute, the largest gamma is larger than the largest beta. And for j equals 2, it means the sum of the two largest gamma is larger or equal than the sum of the two largest beta, and so on. So this is the definition of majorization. And it essentially, a vector majorizes another vector if it's less uniform. So the more uniform you have, so the sum is always 4, but say 4, 0, 0, 0 majorizes 3, 1, 0, 0, and so on. And two vectors majorize each other, so the relationship is symmetric if and only if one is a permutation of the other, as was clear. Okay, so these ideas go back to the early 20th century, and they originated in the study of economic inequality, because looking at these factors as distributions of wealth, and studying how well wealth is distributed across the population. Another fundamental concept here, which I'll need to prove these results, is the notion of sure convexity. So a function is said to be sure convex if the following thing happens. If one vector majorizes the other, then the function for the vector that majorizes the other is larger than for the one that's majorized. So essentially, a function is sure convex if it takes smaller values when its argument is more evenly spread than for some other argument. Okay, so it favors, in a sense, it favors more uniform distributions of the values for the same total sum. And we say that it's strictly sure convex if this inequality is strict whenever gamma majorizes beta, but not the other way around. So it's not one is not a permutation. Okay, so in a sense, as I was saying, sure convex functions favor more uniform vectors. So they essentially they measure inequality. If it's large, it measures it means that there's a lot of inequality, like Gini index and entropies and all these functions. So it is known that symmetric convex functions are sure convex. So symmetric meaning they're invariant in the permutations of the arguments. For example, the L1 norm is sure convex because, of course, it's convex and it's invariant, and it's symmetric, but it's not strictly convex. It's not strictly convex, neither strictly sure convex. And the L2 norm and the Shannon entropy, for example, are strictly sure convex. Actually, the negative Shannon entropy, not the Shannon entropy. And finally, the last notion I need is something called the that's classical. It's called the Pigou-Dalton transfer, which you can think very simply as follows. If you have two wealth distributions, we have one wealth distribution, say beta, and you find two people in that distribution, and you take a little bit of money from one, the richest of the two, and you give it to the poor. And so because of that, this is called a Robin Hood transfer too, because you take from the rich and you give to the poor. So in essence, you find two individuals, one is richer than the other, you take a little bit of the money of the richer of the two, you give it to the poorer, but not too much so that they don't invert their position in the ranking of wealth. Okay, this is called the Pigou-Dalton transfer. And so with the Pigou-Dalton transfer notion, we were able to define, so this is a new definition that we introduced in 2016, something called the strong sure convexity. So we say that the function f is strongly sure convex if whenever gamma majorizes beta, because it resulted from a Pigou-Dalton transfer. And so notice that if you take a vector beta and you apply a Pigou-Dalton transfer, you always get another vector which majorizes the first one, or which is majorized by the first one, actually, which is more uniform. And so whenever the Pigou-Dalton is size epsilon, then the difference between these two functions values is lower bounded by the size of the transfer times some constant that is a feature, a property of this function. So this is called strong sure convexity, as far as we know, was a new concept then. As in standard convexity, strong sure convexity implies strict convexity, but not the other way around. And the key observation, which underlies all the next results, is that these owl norm, so these omega that I introduced, is strongly sure convex, with a constant of strong convexity, which is given by the minimum of the difference between two consecutive weights. So remember that this norm is defined with a weight vector. This weight vector needs to be a non-increasing sequence of weights. This should be a W there. And so the difference between two consecutive, the vector of difference between two consecutive weights, the minimum of these is called the strong convexity parameter of this function. Of course, if you have two weights that are equal, this is no longer strong sure convexity. So the L1 norm is neither strongly nor strictly. So that the L2 norm and the elastic net regularizer are strictly sure convex, but they are not strongly sure convex. That's a key observation. That's what makes the owl qualitatively different from the elastic net. And this lemma is the key to proofs that I'll show you a couple of theorems, but I will not spend a lot of time explaining them, but you kind of guess where they come from these notions. So let's go down to the corollary, which is probably the simplest. Suppose you have a design matrix X, which has undergone the standard operation of extracting the mean, so standardizing. You have 0 mean columns and unit norm, so you have normalized the data. And now if you don't know the correlations, you don't need to know. What we can show is that if the correlation coefficient between two components, two variables y and j, satisfies this property, means this correlation is high enough, okay, close enough to 1, so that this inequality is satisfied, then it's guaranteed that you get exactly equal coefficient estimates for those two variables. So this is we call these exact grouping or exact clustering conditions. And of course, if they are negatively correlated, what happens is that the coefficients are the same, but with symmetric signs. Okay, and we can show these for squared loss, so for linear regression, for L1 loss, for robust regression, same thing. Well, the result is actually a bit stronger for the L1 loss. For logistic loss, it looks very similar. Again, it's always the same. Whenever the correlation is high enough, you're guaranteed to have exact clustering condition in the coefficients estimates. Okay, so just a few remarks about this. So exact grouping. So if you wanted to actually find so one very important thing is that for this to be true, you don't need to know the rows. So the rows, the correlation coefficients between the variables, you don't need to know them. You just need to know that if they're larger than something, then this will happen, without having to estimate these correlations. Okay, if you wanted to estimate them explicitly to do this clustering, this would cost order p squared, because you need to compare all with all the p variables. Whereas solving this problem, I'll show you in a second, scales is p log p, and so from p squared to p log p, when p is of the order of thousands, it's a huge difference. Okay, so this is much better for large p. Another thing is that OWL uses the responses, so it's not. Clustering is not only a function of the correlation itself. It depends also on the responses, because you're solving the supervised learning problem, which has this solution. Okay, so now we also have some statistical bounds, which I will skip because I would have to introduce a lot of notation, and the result is a bit complicated to explain. So I'll skip that. I'll just talk a little bit about how to solve these problems. So. From an optimization perspective. So there are essentially two interesting ways to address this regularized supervised learning problem. So you have a loss function, and you want to minimize the sum of the loss with the regularizer with some regularization parameter. And you can also I like this designation. So this is usually called the Tikhonov regularization structure, where you add a regularizer to the loss, or an Ivanov regularization, where you minimize the loss subject to an upper bound on the regularizer. If everything is convex, if L is convex and omega is convex, these two problems are equivalent in the sense that for any tau, there is a choice of epsilon such that the solution of the problems is the same. Although this is just in theory, because it may be finding this epsilon to transform this problem into this one, or vice versa, may be as difficult as solving the problem itself. But still, there is no loss in generality in using one or the other, because in the end you will need to adjust epsilon or adjust tau in practice. So depending on the problem, you may choose one of these two formulations. So under normal conditions, these are all equivalent. So the way we typically attack Tikhonov regularization is using something like proximal gradient algorithms, which I'm sure you all have seen before. So the way proximal gradient works is that you start wherever you are. So beta t is your current estimate. You compute the gradient of the loss. You take a step in the negative direction of the loss, and then you compute the proximal operator of the regularizer to that. It's called a proximal gradient, or it goes by many different names: iterative shrinkage thresholding, or forward backward splitting. It was reinvented at least 5 times in different communities. But to solve these, you need this notion of proximity operator, which was introduced by Moreau in 1962, which is exactly sort of the same as this problem, but with a particular case where this is just a square Euclidean norm of the distance between the argument of these so-called procs and your variable beta. Okay, and what we so of course we also need the gradient of the loss, but this is simple. Nowadays is assumed to be something very simple. Well, for linear and logistic regression, this is classical expressions for these. For linear regression, this is just a linear operation, just because it's a gradient of a quadratic function. For logistic regression, it's more complicated, but it also has a closed form. And even if you're dealing with a very complicated structure like a deep network, you can compute this gradient. You assume that you can compute this gradient using backpropagation and all these modern tools for computing gradients of complicated functions. You can accelerate the method, but I will skip this. So skipping details, I just want to tell you, I'm not going to derive these, but I'm going to just convince you that computing this proximity operator is quite simple. So essentially it amounts to this. So if we define the monotone cone, it's a vector of it's a set of vectors in our P such that the components are ordered in non-increasing order. That's all we need to know. And let's call this matrix S. Let this matrix sort of P or S, it doesn't matter. It's the vector permutation matrix that puts the arguments of some vector in decreasing order of magnitudes. So to compute the prox, all you have to do is very simple. You throw away the sign, you keep it of the sign of the components, you sort it in decreasing order, then you subtract the weights of the norm, then you project back onto the monotone cone, because when you do this subtraction, you may violate this property because these W's are different. It's just a vector of numbers. Then you need to project back on the first orthant, because you know that you're dealing with non-negative quantities because it's absolute values. Then you need to undo the permutation that led to this sorting here. And then in the end, you put back the signs that you took. So this is very cheap to do, because the most expensive operations are projection on the monotone cone, which is something that is used in an area of statistics called isotonic regression. It costs order P, an famous algorithm called pool adjacent violators. And of course, you need to sort to get these, and sorting costs P log P. And so everything else is P. Projection on the orthant costs P, and component-wise products cost P. So this is a very cheap algorithm. A very cheap step. And the same thing happens for the projection. I'm not going to talk about how it's done, but we can also show that the Euclidean projection on a ball of this norm also costs P log P. And just show you a nice picture because I'm running out of time. It's easy to draw. This is called an atomic norm. It's easy to draw level curves of this norm in any dimension and to come up with the exact expressions for the coordinates of each of these vertices of the norm. So in 2 dimensions, in 3 dimensions, and in any dimension. It's easy to come up with where these are, and then the collection of all these points is just a permutahedron. Just permute and switch signs of these vectors. So this is useful when you're dealing with an algorithm called Frank-Wolf or conditional gradient algorithm, because again, there you need to solve a problem which is called a linear minimization oracle, which is given some vector u, finding the vector in a ball of this norm that has the highest inner product with that vector u, and this again can be solved with cost P log P. Okay, it's easy. So now I would talk a little bit about extensions and applications. I will not have time to do. I'll just talk about one application, one modern application to conclude the talk in a more modern flavor. So it's known that weight sharing is fundamental for the good performance of deep networks. For example, convolutional neural networks use these very, very intensely by the fact that they use convolution, so sharing the weights spatially. But we started out thinking, okay, why don't we use OWL to try to learn the sharing of the parameters of the network directly from the data rather than having to impose this sharing? And when we did these a couple of years ago, this was a paper that I cleared in 2018. And so the idea is that if you train and if you include this, so this growl is this OWL norm, but for groups, for columns of a matrix rather than just for a vector. I won't have time to explain how it works, but it's a very similar idea. It kind of tries to cluster together columns of a matrix rather than just components of a vector. So we add these. It's still true that we can compute the gradient of these and the procs and the projection. Everything we want from the optimization point of view is cheap. And so what we do, we do training, and then once we do training, we identify cluster information. So we identify which components were tied together, were said that they should have the same value. We add and also sparse, because some of them will be zero. So we go from here to here where there is sparsity. So some connections are gone, and there is sharing. For example, these two red lines, of course, it's just an illustration, share the same value. And then we retrain under this constraint that these two red values are the same and there's sparsity. And in the end, we have this parameter shared sparse deep neural network. And what we showed experimentally in a set of data of experiments is that we can reduce significantly the number of unique values. So we have high sparsity and high parameter sharing with only a very small decrease in accuracy. And so this is important for several different reasons, just as economy of parameters, if you want to implement these networks in a low resource hardware and things like that. Okay, then another application would be subspace clustering, but I wouldn't have time because I used all my time. So I'll just conclude. So a final summary. So we started with Oscar, which was a regularizer that was able to identify groups of correlated variables. And we extended it and found out that it was part of a more general family called OWL, norm. We were able to prove, and so of course there's papers, if you're interested you can read about it. I'll be glad to send you the papers. We able to show these exact clustering conditions. Under what conditions are we guaranteed to get explicit identification of what are the correlated variables. We also have the statistical sample complexity bounds that I didn't explain. From an optimization point of view, this is a very benign regularizer. It costs a little bit more than an L1 regularizer, but not much more. So it goes from order P to order P log P in terms of cost. Everything you may want to do with it, like computing proximity operators, Euclidean projections onto all balls, linear minimization oracles, they all cost P log P, order P log P. And then I talked a little bit about extension. So there's several applications. People have used these in different areas. And I think it's a promising, it's a useful addition to the toolbox of regularizers for supervised learning. And thank you for your attention, and I will be glad to answer any questions.
Okay. Thank you very much, Mario. Any questions? Anyone would like to do a question to Mario? Well, while people think or type the question, I think in a way you have answered the question that I had for you, but I will do it in any case. So quite recently, I heard someone saying that with deep learning, we don't need feature selection anymore. Would you like to comment this phrase?
Yeah, well, in deep learning, depending on exactly what you're doing, you're essentially doing feature learning rather than, so you don't start in this situation where we have feature selection, where you have features that you need to select a few. But if you from a more generic perspective here, you look at, say, the second layer of a deep network, the things that come from the first layer are features that are being learned at the same time. And so there you have it's known that you have a strong correlation. And so this was the starting point for this recent work or more recent, not so recent, work that maybe in some layer of the network, you're being fed you're being given features that come from the previous layers, and these features have high correlations. And so maybe you need to tie the variables together, or maybe sparsified. So that's why people use sparsity regularizers in deep networks, and we can use OWL. And L1 regularization is very common in deep networks to try to throw away some weights. This actually comes from the 90s. There's this this method which uses L1 regularization to actually deactivate some nodes, which was called, a nice name, it's called the brain surgeon, because you're extracting some neurons from the brain of the network. It's called the optimal brain surgeon. And so, yeah, no. It depends on what you mean by features, but deep networks are essentially a cascade of features, and there's a high need for feature selection inside the networks.
Thank you very much. So I think if there isn't any more questions, we can stop here. Thanking Mario once more. And I think we'll have a break for lunch and we will return at 2:30. Am I right, Alexandra?
Yes, and since my students and our students asked me to create some breaking rooms where possibly the attendance the attendant can ask questions and do discussions with the speakers. So I will now create